Assalamualaikum guys, my name is Sayyid Zain Mahmood and currently I am studying physics in University of Gujarat. I am working under my respected instructor Mr. Muhammad Bilal Tahir, and today we shall talk about a practical an experiment which shall prove theory of induction. First of all, the phenomena of induction was firstly observed by Faraday, and he did 3 experiments. In one, he took a coil and placed it in magnetic field. He moved the coil towards right and observed current produced in one direction. Secondly, he did the same. He took a coil and placed in the magnetic field and moved in the opposite direction, and he observed that current again flows but in opposite direction. In the third part, he took a coil and placed in the magnetic field. He neither moved it to the left nor right, but he varies the speed, varies the strength of magnetic field, and a current again produced. By these 3 experiments, he concluded that a current, an EMF, will induce in the coil whenever the magnetic flux to the coil is changed. So, for proving these 3 phenomena, we have designed a practical titled as Verification of Theory of Induction. So here is our practical theory of induction. We have 4 points. First one is area of the coil. These 3 practicals tell us that area of the coil matters when you are talking about induction. Secondly, we have number of turns. When you have larger number of turns, you have larger current. When you have lower number of turns, you have lower current. Third, we have the strength of magnetic field B, or the magnets we are using in our practical, you may say that. So whenever the magnetic field is changed, whenever the strength of magnetic field is changed, the current produced in the coil is changed. I shall quote an example at the end, but first we talk about our 4th point, that is speed of rotation. Similar to this practical, the speed matters when Faraday moved his coil towards right or towards left. In our practical, we are moving our coil with a DC motor. So the rotation of DC motor also affect the current produced in our coil. So now I am quoting an example. The design of our practical includes 2 magnets attached with a rotating unit, and this rotating unit is further attached with a DC motor. When we apply current to DC motor, it rotates and magnet rotates. We place our coil between these 2 magnets, and we shall connect our meter with this and shall get our readings. So now I have explained the idea of our practical, the theory of Faraday's law, and the title, I have explained the title of our practical. So now have a look on apparatus and the procedure of. So here is the theory of our practical, that is, we are going to prove the theory of induction. In theory of induction, we are going to prove these 4 points. The first one is that the motional EMF produced in the coil is directly proportional to number of turns of the coil. As you can see that here we have 4 coils with different number of turns. Secondly, area of the coil. We have different coils with different area. And the third point is the speed of rotation. We shall vary the speed of rotation of our magnets, and through that we shall prove that induced induction or induced EMF is directly proportional to speed of rotation of the coil. And the last point is strength of B. After proving these 4 points, we shall draw graph between area and voltage and the number of turns and voltage. So here are our apparatus, our components. So these are the 4 wires we are going to use in this experiment, and this unit we have made it by ourselves. In this unit we have 2 ferromagnets and a DC motor of 9 volts. This is supposed to rotate this unit with 9 volt battery which we have here. This is the stand which have a pin over which we are going to hold our these coils. Besides that, we have a multimeter and a tripod stand to hold this motor here in air. So first of all, we are going to hold our this unit with this tripod stand. Set the appropriate height. After that, I am to attach our first coil. This coil has 20 number of turns and have small area. I am going to attach this coil here on the pin. With its terminal, I shall attach my voltmeter. After attaching the voltmeter, you can see here these are stray voltages. So you have to wait to first stabilize of this value. After, when we shall get our readings, then we shall minus this value from our reading, and then in this way we will get our required accurate value. So these are the stray voltages, perhaps due to the magnetisms in our surrounding. As you can you see that there are many wires going around in lab for electricity and for other purposes. So these voltages are due to that stray magnetic fields. So as you can see, this voltage is now stabilized and it is 1.6 millivolt. I noted it down on my notebook. Here, stray voltage, and here after rotation voltage, or you may say that it is EMF. So we are getting 1.6 millivolt at trace position, and now I am going to attach this battery with our motor so to rotate our unit. Just focus it here. So as I attach my battery, you can see that reading is changing rapidly. We shall count the maximum reading we get from here. As you can see that we got 30 millivolt while rotating our unit. I shall explain later why this voltage is not stabilized at a point, why this vary within a second from it so many times. I shall explain it later. But first we see that we have 30 millivolt of maximum voltage we get from this coil. And here I explain that this coil has 20 turns and have small area. So after our first reading, I am going to replace this small coil with this coil. The area of these two coils is similar, but this small coil has 20 turns and this coil has 60 turns. So now we are going to perform our experiment with this larger coil. So I have attached this coil on our pin. So again, I am going to attach my multimeter. And then I shall count for the stray voltages. I shall wait for this value to stabilize. As you can see that for this coil, this value is stabilized so quickly, and we got 0.8 millivolt for this larger coil. This coil has 60 turns and have small area also. So now I am going to lower this unit over the coil. So as soon as I attach this battery to our unit, this rotating coil produces maximum of 15 millivolts. So after getting reading from this coil, I shall repeat the process for these two coils. This coil has 60 turns and have larger area. This coil has 100 turns and larger area. Stop. So now as soon as I attach my 9-volt battery with this motor, this unit is going to rotate, and you can see that we can get up to 28 millivolts, maximum of 28 millivolts with this rotation. So I write it here, we got 29 millivolt maximum. So as you can see, for this coil our stray voltage is stable at 1.5 millivolts. This coil has 100 turns and have large area. Similarly, I attach my battery to motor, and after rotation you can see that this produces up to 47 millivolts of electric current. 48. So we got 48 millivolts of electric current. So these are our readings. By these readings we shall prove that EMF induced in the coil is directly proportional to the number of turns, area of the coil, strength of magnetic field, and our fourth point is rotation speed of motor. So here are those 4 readings we took. This is the number of coil column. This column represents area of the coil. We have 2 standard here, small and large. The DC motor we are using revolves at 200 RPM, and these are the corrected values of voltage. These are the voltage values, and these the trace voltage. When we subtract stray voltages from the value we took from voltmeter, we get the accurate value of voltage. So this is the graph I have made for these values. These along the y-axis are the number of turns of the coil, and along the x-axis these are the volts, millivolts. So graph shows that when the number of turns increase, voltage increase. In other words, number of turns and the voltage are directly proportional to each other. This portion represents that when you have equal number of turns but area is larger than this coil, then you can get more voltage at the same number of turns. I received a question about the practical that why we don't get a stabilized value on multimeter while performing the experiment. So now I'm going to explain the reason. Actually, the induction or the EMF produced in the coil is directly proportional to the number of field line passing perpendicularly through the area of the coil. So you suppose that this is the coil and this is the magnet. Magnet is supposed to rotate around the coil. When magnet is at this position or on the back of the coil, you see that maximum area of the coil is exposed to magnet. It is in this position. This is the coil and here is the magnet. So maximum field lines can pass through the coil. But when magnet is rotated and approaches to this position, if you see from this angle, the coil is now appears to be flat. From this angle, coil doesn't appear as circle, it appears like a single line, and here is the magnet. So there is negligible area exposed to the magnet, and the minimum number of field lines pass through the area of the coil. So at this position we get maximum current, and at this position we get minimum current or minimum EMF. So that's the reason why we don't get a stabilized value on multimeter while performing the experiment. So now any of you might think that in actual AC generators or the devices which are supposed to produce current give us a stabilized value of voltage and current. So in our experiment, why the value is not stabilized? The reason being that in actual AC generators there is not a single coil. There is a number of coils. When one coil approaches at the blind spot of magnet, the other coil balances its effect, and that's why the voltage we get from here is stabilized. Another reason of stabilized value of an AC generator is also that it rotates at a very high speed. The rotation of an ordinary household AC generator is 2800 RPM. It is driven with an engine, a piston engine which can rotate the coil with a very high speed. But in our practical, we are using a DC motor. The speed of a DC motor is not enough to rotate our unit at the speed to get a stabilized value.